Good morning, everyone. I am Shivani, and I welcome you all for the summary session of the course of Simulations of Communication Systems using MATLAB. So, in this session, I will be taking up some doubts which were asked by you people till the end of this week. So, I had requested in last and the lecture before to submit your doubts in the question and answer portal. So I have few questions which people have posted in the portal that I'll be taking up. So those are mostly some assignment questions. So I'll try to provide some detailed solutions for them. And some questions are repetitive, like I have solved them in previous sessions. So if I am out of time, I'll direct you to the particular lecture and the question number which you should refer for the solution of that particular question. Otherwise, I'll be solving them in detail in this session. Okay, so let's start with the first query that you have posted. So this was the first query that was posted. So it says that given that the symbol AM is transmitted from a Comm constellation in presence of a zero mean circularly symmetric AWGN with various variance and not, then the received symbol is Gaussian distributed with mean what and variance what. And these are the four options with you. Okay. So what is given to us is we have AM as the symbol being transmitted. Okay. And this AM will be a complex number. Then you will receive YM. So this AM will be from a Comm constellation. So it will be like some CM into e power j theta m format. Okay. So it's a complex quantity. And then you have YM. So this is transmitted symbol. Therefore, received symbol is Y, which is whatever you are transmitting AM plus your AWGN noise W, where W is Gaussian with zero mean and variance and not. And it is given to us that this particular noise, whatever we are having, is zero mean circularly symmetric Gaussian with variance and not. And yeah, this is what we have. And yeah, one small thing that you need to consider here is the statistics you need to find given AM. So everything is given AM. Okay. So now you have this particular equation here. You have this YM as AM plus WM. Since we are given, sorry, not M, since we are given AM, so this particular quantity is given, which means it is constant. So if this is a constant and this is a Gaussian random variable, and if we add any constant to a Gaussian random variable, it shifts its mean. And since it is a constant, it does not change its variance. Okay, so what we will do is we'll figure out one by one what is happening here. So we have expectation of Y given AM. This is the first thing that we need to find. So it is Gaussian distributed with mean what and variance what. Okay, so we need to find this mean expectation of Y given AM. So this is equal to expectation of, what is your YM? YM is AM plus W given AM. This is equal to, if you apply linearity, it will be expectation of AM given AM plus expectation of W given AM. Now here, this particular thing is simply equal to AM, and this is equal to your expectation of W, since your noise is independent of what you are transmitting, that is AM. Okay, so this is what we are getting. So we have AM plus expectation of W. And what is mean of your W? Expectation of W, it is a zero mean random variable. So therefore expectation of W will be equal to 0. So this comes out to be equal to AM. Okay, so this is your expectation. So what we found out is expectation of this quantity comes out to be AM. Now we need to figure out what is your variance. Okay, so therefore variance of Y is equal to expectation of Y minus expectation of Y, which is AM, given AM. Yeah, so this is given AM. Okay, now your Y equal to A plus M, which means that your W will be equal to Y minus AM. So here your Y minus AM is simply equal to W. So we get this as expectation of magnitude W square given AM, which is equal to expectation of magnitude of W square. Why? Again, same reason, since W is independent of AM. And what is this? Since this is a zero mean, this is equal to your variance of W. Since W is zero mean, so this comes out to be equal to N naught. So therefore the variance is N naught. So what we get is the mean is AM and the variance is N naught. Okay, so this is the correct answer. Any questions? Okay, if there are no further questions, I'll move on to the next question then. Okay, so this is another assignment question which was there. Okay. So what does this question say? So it says that 8PSK can be represented as a dash dimensional signal. So what do you mean by dimension of a signal? So first thing is, what is dimension of a signal? So let us go to signal space representation that we had. So suppose a signal x of t, which is equal to okay, can be completely represented using n basis functions let's say phi n of t, where n is equal to 1 to capital N, such that x of t is equal to summation n equal to 1 to n a n phi n of t. Then x of t belongs to the signal space spanned by the basis phi n of t, n equal to 1 to n. Okay. And this space has a dimension n, which is equal to number of signals or functions in the basis set. Okay. So we can take it as an analogy to your vector space also. So if you have a vector which is 1 or 1, 2, so you can represent it using two bases. So this you can write as 1 into 1, 0 plus 2 into 0, 1. So these two are your bases and these are your coefficients. So you can write it in as a combination, linear combination of two basis functions or vectors here. Same thing here. And the number of basis signals in your signal for that particular signal space is known as n. Okay. So now in low pass equivalent or in equivalent low pass, AM, or let's say in this way, mth signal or mth point of 8 PSK is given by AM equal to e power j 2 pi m minus 1 by 8, which is equal to e power j pi m minus 1 by 4. Okay. So this is what you have, where your m is from 1, 2 and so on till m. Okay, so this is your constellation. So the signal or the bandpass signal that you will be transmitting or that we will transmit will be SMT equal to real part of AM into e power j 2 pi FCT, which is equal to real part of AM is e power j 2 pi m minus 1, or rather pi by 4 m minus 1 into e power j 2 pi FCT. Okay, and now you can write it as real part of e power j 2 pi FCT plus pi by 4 m minus 1, which comes out to be equal to cos of 2 pi FCT plus pi by 4 m minus 1. Okay. Now this you can write as, this is cos of a plus b, so using cos of a plus b, which is equal to cos a cos b minus sin a sin b, what we get is SMT is equal to cos pi by 4 m minus 1 into cos of 2 pi fct minus sin of pi by 4 m minus 1 into sin of 2 pi fct. Okay, so now what we can do is, so this is a signal that we are having, this is the mth signal that we are having. So now I can just rearrange it a little bit. I can write it as under root t by 2 cos pi by 4 m minus 1 multiplied by under root 2 by t cos of 2 pi fct plus under root t by 2 sin pi by 4 m minus 1. Then we'll have minus 2 by t sin 2 pi fct. So this we can write as is equal to am1 phi 1 of t plus am2 phi 2 of t, where am1 is under root t by 2 cos pi by 4 m minus 1 and am2 is under root t by 2 sin pi by 4 m minus 1. Moreover, here phi 1 of t is equal to under root 2 by t cos 2 pi fct, and phi 2 of t is under root 2 by t with minus sign sin 2 pi fct for t belonging to 0 to t, and your t is some integer multiple of 1 by fc. Okay. Yeah. So now the question is, are phi 1 of t and phi 2 of t linearly independent? Let's just check orthogonality. If they're orthogonal, then they are linearly independent. And are they, or to be very specific, are they orthonormal? This is a quicker way to go around this. I know these are bases, that's why I'm going it in this way, but a more better approach for unknown things will be to go with Gram-Schmidt. Let's not go into that for now. So let us first check inner product of phi 1 and phi 2. Is equal to integral 0 to t minus 2 by t cos 2 pi fct sin 2 pi fct dt. So 2 sin a cos a is sin of 2a. So this will be equal to minus 1 by t integral 0 to t sin of 4 pi fct dt, which is equal to minus 1 by t cos of 4 pi fct upon 4 pi c from 0 to t. This is equal to 1 by t. Then you have cos of 4 pi, your k fc is your, okay, fc, your capital T is k by fc minus 1 upon 4 pi fc. Since this is integer multiple of 4 pi, this is also equal to 1, so this comes out to be equal to 0. Okay, so now we have, these are orthogonal. Okay, then let us check this thing. In a product of phi1 of t with itself, that will be equal to 2 by t integral 0 to t cos square 2 pi fct dt. This is equal to 2 by t, it is cos, so integral 0 to t 1 plus cos 4 pi fct by 2 dt. This 2 gets cancelled. Then we have 1 by t. Integral of this first part is simply equal to t plus integral of this is sine of 4 pi fct upon 4 pi fc from 0 to capital T. So this comes out to be equal to 1 by t plus sine 4 pi k minus 0 upon 4 pi fc. So this comes out to be equal to 0. So this is equal to 1 by t into t, which is equal to 1. So this is unit now. Similarly, you can find in a product of phi2 of t with itself. So that will be also equal to 2 by t integral 0 to capital T sine square 2 pi fct dt. Okay. So again I can write it as 2 by t integral 0 to t 1 minus cos 4 pi fct upon 4 pi fct upon 2 dt. This 2 gets cancelled. Integral of this part is 1 and integral of this part we have seen here comes out to be equal to 0. So therefore again this comes out to be equal to 1 by t into t, which comes out to be equal to 1, which means that phi1 of t and phi2 of t are bases, are orthonormal, and can be used to represent all 8 PSK signals, which means dimension, which means phi1 of t and phi2 of t are bases. Therefore dimension of 8 PSK is 2. Another simpler way to look at it is just look at the equivalent low pass signal. Now consider only the equivalent low pass signal. So we have this Am as e power j pi m minus 1 by m, and here m is m was 8, this comes out to be equal to 4. This you can write as cos of pi by 4 m minus 1 plus j times sine of pi by 4 m minus 1. So this is a complex number. This is a complex number, and a complex number has a real part and an imaginary part. Okay, so this is its real part This is its imaginary part, real part and imaginary part. If you draw a complex line, this is your real part, this is your j times imaginary part. Okay, so this is your real axis, this is your imaginary axis, both of them are orthogonal. So you have two different directions, two different orthogonal directions, which means you have two different dimensions to look at. So therefore it is two-dimensional. Okay, so the answer for this is, it is a two-dimensional signal. Is it clear? Any questions here? Let me move on to the next question. So the next question says, an increase in the noise variance leads to an dash in the ambiguity of the received signal. So option is increase in the ambiguity or decrease in the ambiguity. Okay. So what happens when your noise variance increases? So let us try to understand using the PDF of probability density function of. Okay, there is some issue, I think so. Yeah, okay. Now it's visible. Yeah. So an increase in the noise variance leads to an dash in the ambiguity of the received signal. So let us try to understand what happens with increase in noise variance. Okay. So with the help of PDF. So let's say x is a Gaussian random variable with, let's say for general, for the sake of convenience, 0, and variance, let's say sigma square. Okay. So this is 0 axis, and let's say it has some variance. So this is its PDF. Now suppose I reduce its variance. So this is for sigma 1. Now suppose I reduce the variance. So what will happen? Your signal will become something like this. The PDF. So this is your PDF, fx of x, which is PDF of x. Okay, so this is for sigma 2. So what is happening is your sigma 1, sigma square variance. Sigma 1 square is greater than your sigma 2 square. So if variance increases, the PDF spreads more. It spreads more. What do you mean by that? It means that the values that are here in this tail, probably in this particular region, or if we look at the region here, whatever values of x that are present here, little x are present in this region, have a higher probability of occurrence for this particular, for this red curve where your variance is larger. So if your spread, noise spread is larger, then you will be getting, you might get larger values with a higher probability. However, if your variance is small, then it will be less. So how does it look in general? So this is your 0 point, and if I'm having, okay, This is your 0. So what will happen is, for your red curve will be something like this. Lot of points near 0, but still there will be points which are there in this region as well. Something like this. It will reduce like this symmetrically. So occurrence of these points will also happen. However, for this purple line where the variance is small, you will be crowded more near the 0 point like this, and then you will decay faster. Okay, so here the noise values at higher will be very small, very less. Let's reduce it further also. Something like this. Okay, it will be concentrated more towards 0. So what will happen if we have higher noise variance? And let us try to understand it more in MATLAB. I forgot to initialize it actually. We initialize MATLAB. And share my screen. This was done in class, but still let's do it again. It's okay. So let me start sharing. So let us do this. We'll take example of PSK. So let's say we have n equal to 1e plus 6, or let's say 3 only. So these are your number of realizations. Then n naught is equal to, let's say 1, which is your noise variance. Then let's say we have E, again let us keep it as 1, which is your energy of each constellation point. Then you have M equal to, let us take 4 for now. So this is your number of points in constellation. Okay. And then let's say SM, let's be consistent, AM is equal to e power j 2 pi m minus 1 by, or let's do it in this way, 0 to capital M minus 1 divided by m, and let's multiply it by square root of e. Okay. Let's run this now. Okay, and let's do plot real part of AM, sorry, not AM, by comma imaginary part of y. What is your y? Y should be your received signal. Let us define the received signal now. So your y will be equal to am plus your noise. And now let us generate your noise is and n and dimensions n comma 1 plus j times rand n comma 1, and now I need to modify its variance as well. So this will get multiplied by square root of n naught by 2. Yeah, let us run this and see what happens. So check ambiguity. Okay. So should I give? Did I do now? Sorry. Is it happening like this? Oh, sorry. These are your constellation points. We need to generate AMs. We need to sample randomly from each of these 4 points. Extremely sorry for this. Extremely sorry. This is wrong. So we need to take random indices, n random indices from this. Now let us see how it looks. This should be n, then there should be n comma 1. This should be okay. Is it happening like this? Let's do this. Dimensions are weird. Make this very small first. Oops. Yeah, so these are the 4 points that we are having for the constellation. Okay, so when I'm having very small noise variance, when I'm having it at 0.0001, it looks like this. Now suppose I increase the noise variance, it looks like this. So it has spread more. It has spread more. Now if I can increase it, it looks something like this. Now if I make it, let's say 1, it looks like this. So can't even recognize what is happening here. There are 4 constellation points. We don't know where they have gone now. It's all mixed. So the ambiguity with for which ambiguity, whether the point which you have received here, or let's say received here, it belongs to this particular constellation or this constellation, is difficult to see. Okay, now in similar way, let's keep this noise. So what we have seen is if we increase noise variance, the ambiguity increases. Now suppose I keep this noise variance as it is, and if I increase the energy, so it is like this now. Now if I increase it further, let's say I make it 6. So again, now they are much more separable. They are spread out but separable because their energy is increased. So if I increase it further, it looks something like this. It will separate out more. So the ambiguity again reduces. So if I reduce the noise variance, if I increase the noise variance, the ambiguity increases. If I increase the energy, the ambiguity reduces. Okay, I hope this is clear. Let me go to my notes now. Okay. Yeah, fine. So like this, it's happening. Now, if you can also look at it through VPSK perspective and decision rule. So if I have VPSK, that is I'm transmitting plus minus root ES, and I have this AWG and Gaussian noise, then here conditional PDFs for your decision rule, you need to have your likelihood ratios. So this is your F PDF something. So you will have two likelihood ratios. One will be this one, which is something like this. Okay, we draw it. So this is your decision rule. So this is your under root minus under root ES. This is your under root ES. This side is your conditional PDF of y given root minus root ES, and this is the region of y given under root ES. And what you do is, in this region you decide in favor of ES, and in this region you decide in favor of in this green region you decide in favor of minus under root ES, and in this blue region you decide in favor of ES. Now if you see this particular value or the region of or the PDF of the conditional PDF corresponding to ES is having larger values for this red in the region of minus ES, and similarly here. So the probability of error here will be larger. So it is more likely that the value of y, which corresponds to your minus ES transmission, is detected as ES. So the ambiguity again is higher, which can be seen from this figure. So what we have seen is the ambiguity increases. So there is an increase in ambiguity. Is there any question here? Okay, if there are no questions, then I'll move on to the next question. So this question says that an increase in the signal variance leads to an dash in the ambiguity of the received signals. So we saw here that if we saw in the MATLAB code that if we increase the signal variance, signal variance means signal energy, it leads to a reduction in ambiguity. So the ambiguity in this case decreases. Okay. Another way to look at is based on your maximum likelihood ratio rule in similar way what we have seen here. So let's say I have two energies, ES and minus ES1 and ES2, and let's say your ES1 is greater than ES2. Okay, so then let's say we have BPSK, This is what we are transmitting. So we will be receiving 1 minus under root ES1 plus noise, or if for ES1 as energy, and we'll be having y equal to plus minus under root ES2 plus noise when we are having ES2 as energy. So again, given ES1 and ES2, yeah, the conditional PADFs will have Gaussian with same noise variance but different means. Okay, so let us try to see how those will look. This is your 0. Okay, so let's say this is your minus root ES 1, and here you will have your under root ES 1. So we'll have something like this. Similar way, let me just copy paste this. Will be here. Something like this. It should be symmetric. I may not look symmetric, but it should be symmetric. Okay, so this is for your ES1, and same thing when we are having ES2. Your ES2 is smaller than your ES1. Let's say it is here, like this. So now you will have something like this. Same variance. In here, same thing. So now what you observe is, for this brown line, or for ES2, this overlap here is larger. So again, these two PDFs, this red PDFs are well separated. However, these are not well separated. So again, you have a higher ambiguity. So therefore, as energy increases, your ambiguity reduces. We saw this through simulations also. Is it clear? Any questions? Okay. If there are no questions, I'll move on to the next question then. So this is the fifth question. It says that an increase in the number of symbols in a fixed amplitude PSK constellation results in dash 1. Symbols moving closer, 2. Symbols moving apart. So it says that it's having a fixed amplitude. So the energy is fixed. What it means is, your PSK constellation is around a circle, is located on a circle of radius as its energy, as its average energy, and that is its amplitude also. So how does your PSK look? Your PSK signal looks as under root e power j 2 pi m minus 1 by m, capital M, and this m varies from 1, 2 and so on till capital M. So now if you see, your magnitude of Sm is root e, which means these are located on a fixed on a circle of radius m radius E. So as m changes, angle changes. Okay. So how does it change? Let us do that now. So let us take a simple example. So now if your m is equal to 2, then your constellation points lie here and here. Okay, and what happens here is this this radius is your d-min. Sorry, this is under root E, and for this MPSK, your minimum distance is this. So this is your d-min. Okay. Okay, now let us increase your m now. So your d-min will change. Okay, this will go now. So now let us take m equal to 2. M equal to 4. So now what will happen is there will be 2 more points which are located here. Your energy is same, your amplitude is same. Only your capital M is changing, and that's why you're adding more points along the same circle. Like this. So now this is your d-min. Now let us take up same thing, and let us now look at m equal to 8. Okay. So in that situation, we will add 4 more points. One will be here, one will be here, one will be here, one will be here. And now this is your d-min. Okay. So now if you look here, for m equal to 2, this entire diameter was your minimum distance. When you increased your m to 4, this became your minimum distance, which is definitely smaller than your diameter. Then when I increase it further to m equal to 8, the minimum distance is only this much, which is again less than the minimum distance for 4. So what we observe is, as, or let's write it in this way, for constant amplitude, that is for fixed E, As m increases, the minimum distance d min decreases, which means the constellation points become closer. Is it clear? Any questions? So therefore the answer to this question is the constellation points become closer when we increase the number of symbols. Any questions till this part? Okay, if there are no questions, then let me move on to the next question. Okay, so this is also some another doubt which was asked. So it says that given that M symbol PAM constellation is given by A equal to, so this is the constellation that is given to us. So there is dot 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 here. So this is the constellation that is given to us. Its average energy dash with an increase in M. So, and your options are increases, decreases, remains unchanged, and cannot be determined. So to understand this, first we need to figure out what happens to the average energy when for a given M. Okay. So let us calculate the average energy. So what is the constellation given to us? So the constellation given to us is A, which is plus minus 1 by m plus minus 3 by m plus minus and so on till plus minus m minus 1 by m. Okay, so therefore average energy E average is given by summation m equal to 1 to capital M magnitude of Sm square into 1 by m. So we'll assume equiprobable symbols. So this is probability of Sm for all n. Okay. So therefore, average energy is 1 by m into, so if you take magnitude square of plus minus 1 by m, that will be 1 by m square. So I can write it as 1 by m to 2 times 1 by m square plus 3 by m square plus and so on till m minus 1 by capital M square. Okay. So here the assumption is your m is, let's say, an even number. Okay. So like this you have, so you have here 2 by m cube multiplied by, so 1 m, this I can take m 1 by m square common here, so you'll have 1 plus 3 square and so on till m minus 1 square. Okay, so 1 3 square and so on till m minus 1 square. So these are m by 2 or first m by 2 odd numbers, and it is the sum of squares of first m by 2 odd numbers. So sum of squares of first n odd numbers is given by n into 2n plus 1 into 2n minus 1 divided by 3. Okay, so this is what we have here. Just a minute. Okay, just a minute. There is some gadgad here, I think. Just a minute. I think I messed up a little bit. Oops. Yeah, okay. This is correct. Yeah. So therefore, 1 plus 3 square and so on till m minus 1 square will be equal to, these are m by 2. So your little n is m by 2. M by 2 into 2 times m by 2 plus 1. Again you have 2 times m by 2 minus 1 divided by 3. So therefore E average will be equal to 2 by m cube multiplied by m by 2 into m plus 1 into m minus 1 by 3. So 1m gets cancelled here and this 2 gets cancelled. So you have 1 by 3. M plus 1 into m minus 1 is m square minus 1 by m square. And you can write this as 1 by 3 into 1 minus 1 by m square. Okay, so now let us try to understand what is happening here. So you have E average as 1 by 3, 1 minus 1 by m square. So as m increases, it implies that your m square increases. It implies that your 1 by m square will decrease, which means that minus of 1 by m square will increase. So this implies 1 minus 1 by m square will increase, which means that if I scale it by a constant, nothing will happen. So if I add a constant and if I scale it by a constant, the trends won't affect. It will just shift or scale it. Positive constant. Then, so therefore what we see is this E average, which is equal to 1 by 3 into 1 minus 1 by m square, increases as m tends or as n increases. Okay, so the answer is it increases. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay. So this is the next question. So it says that all complex valued one-dimensional constellation or two-dimensional real valued constellations can be viewed as, okay, can be viewed as special cases of PAM, PSK, Comm, or FST. Okay. So it says that all complex valued one dimensional or two dimensional real. So any complex valued, or let's say complex number, okay, complex valued constellation has its mth point as Sm equal to Rm plus J times Im. Okay, so this thing here is in Cartesian coordinate form. Okay, and same thing you can write it as xm into e power j theta m, and this is in your polar form. Okay. Now for a complex valued constellation, you have a freedom of manipulating both of them, like xm and Im, or in Cartesian coordinate, or both, or in your polar form. Either you modify its magnitude or you modify its angle or phase. Okay, so now by modifying this, you can generate any possible complex valued constellation, and we have seen that this particular notation here corresponds to your Comm constellation. This corresponds to your Comm constellation, or even this representation is for Comm. Okay, so now what we can do is we can see that if we make, or if we restrict the cases for your xm, theta m, or in Cartesian form Rm and Im, you will get different forms or different constellations. So now suppose we keep theta m as 0, then your Sm will be equal to your xm. This is simply your PAM. And now if you keep your xm as under root e, then you get Sm as under root e into e power j theta m. This will give you your PSK constellation. So you can see that any complex valued constellation has, or is a special case of Comm. Is it clear? Any questions? Okay. Okay, if there are no questions, I'll move on to the next question then. So this question says that an increase in the spectral efficiency at the same transmitted power results in an dash in the symbol error rate. So this we had seen. So it says, so basically it says that the spectral efficiency will increase when you increase your points in your constellation. So as m increases, it means your spectral efficiency increases. For a given constellation point, sorry, for a given energy or transmit power, as m increases, the constellation points come closer. This reduces, sorry, yeah, this reduce, this increases the ambiguity, and hence this increases probability of error. So you can clearly see from PSK, Comm, like constellations. Okay, you can check it. Okay, so it increases your probability of error. Okay, any questions? Okay, so let me move on to the next query then. So this question says that under the assumption of equal prior probabilities for all the symbols, the maximum a posteriori estimate of the transmitted symbol reduces to the symbol with the dash. So first option is largest Euclidean distance. Next option is smallest Euclidean distance. Next is largest correlation. And the last option is smallest correlation. Okay, so this question I had already taken in week 5. So I'll refer you to week 5. I'll solve it now, but still you can see question 5, sorry, week 10. Question 5 of week 10. I have done this question, but still let us look at it again. It's nice to look at these concepts again. It's fine. So we are talking about AWGN signals. So what we'll say is assumptions, or we'll take very general case. So we'll take M point constellation, SM transmitted symbol, y equal to SM plus N received signal, and N is your AWGN, variance amount. Okay, fine. And okay, let's say it is n dimensional. Not along each dimension. Let's say sigma square. Real dimensions. So therefore, PDF of y given Sm is given by 1 upon 2 pi sigma square to the power n e power minus norm of y minus Sm square divided by 2 sigma square. Okay. So therefore, map rule, or does it say you decide m hat, which is argmax m for 1 less than or equal to m less than or equal to capital M, such that probability that Sm being transmitted given y being received is maximum. So this you can write as argmax of 1 less than or equal to m less than or equal to capital M. Using base rule, this is equal to PDF of y given Sm into f probability of Sm divided by f of y. So this is by base rule. Okay. So now what we have is, so we have this f of ym common for all. So we can ignore. It won't change your argmax. So this is equal to argmax of 1 less than or equal to m less than or equal to capital M f of y given Sm into probability of Sm. Since they are equiprobable and we have m point constellation, it is 1 by m. Again, this thing 1 by m is common for all, or it is rather a constant. So this also we can ignore. So then we'll have this as argmax of 1 less than or equal to m less than or equal to capital M f of y given Sm. So this is basically your maximum likelihood ML. This is your likelihood function. So whatever value of Sm will give your maximum likelihood. That is the thing that you will obtain. So now you can substitute your likelihood function. So then we have argmax of 1 less than or equal to m less than or equal to capital M. What is this? This is 1 upon under root 2 pi n by 2 sigma square to the power n by 2 e power minus norm of y minus Sm square divided by 2 sigma square. Now again, this part is common, can ignore, and what we'll do is we'll ignore common part and take natural log for all m. So this will give me argmax. Since log is a monotonically increasing function, the argmax won't change. Less than or equal to m less than or equal to capital M. So this will be minus of norm of L2 norm of y minus Sm square by 2 sigma square. Now this thing here is a negative value. So what we can do is we can just multiply by the inverse of it and change argmax to argmin. So this becomes argmin of 1 less than or equal to m less than or equal to capital M norm of y minus Sm square. So this thing here is your Euclidean norm, which is given by under root of y1 minus Sm1 square and so on till yn minus Smn square. Okay, so this is what you will be receiving. Okay, yeah. So this is basically your Euclidean distance, which means that this will give you the symbol with smallest Euclidean distance from y. Okay, I hope it is clear. And since it does this, this is known as minimum distance or minimum, say, Euclidean distance. Okay, so what it says is the transmitted symbol reduces to the symbol with the smallest Euclidean distance. Is it clear? Any questions? Okay, now let us move on to the next question. I see one question in the chat box. I'll answer. Yeah. So this is the next question. So it says that the union bound on the probability of error for an M symbol constellation with a minimum distance d min between the constellation points under the noise with variance n0 can be expressed as. Okay. So you need to figure out what the union bound is. So first let us look at probability of error. So this probability of error can be given as summation m equal to 1 to m. You are having m points. Probability that mth constellation point was transmitted multiplied by probability of error given the mth point was transmitted. This is known as law of total probability. Okay, so we have this now. Now, okay, yeah, we have this. Let us say those are equiprobable. So this probability of Sm will be equal to 1 by m summation m equal to 1 to m into probability of error given Sm was transmitted. So let's say this is equation 1. So therefore probability of error given Sm was transmitted will be equal to probability that union m prime equal to 1 to capital M prime not equal to M, Sm gets converted to Sm prime. Any one of this event happens, then there will be an error given Sm was transmitted. So this is less than or equal to summation M prime equal to 1 to capital M prime not equal to M, probability that Sm gets converted to Sm prime given Sm. And this probability here, M prime not equal to M, this is basically equal to Q function of dmm1 upon under root of 2n naught. Okay, I request you to go and check how this comes up. Okay, so now let me substitute this back to equation 1. So substituting this in equation 1, we get probability of error. Now let me write it in next page only. Probability of error as 1 by m summation m equal to 1 to capital M, summation m prime equal to 1 to capital M prime not equal to M, Q of dmm prime upon under root 2 n naught. Okay, now this is less than or equal to, sorry. Okay, now we are given d min as the minimum distance. Okay, so d min is the minimum distance, so therefore dmm prime will be greater than or equal to d min for all m and m prime. Okay, now this Q function is a decreasing function. So therefore Q function of dmm prime by under root 2 n naught will be less than or equal to Q function of d min upon under root 2 n naught. Okay, if I substitute it back here, so therefore probability of error is less than or equal to 1 by m summation m equal to 1 to capital M, summation m prime equal to 1 to capital M prime not equal to M, Q of d min upon under root 2 n naught. Okay, so this becomes 1 by m into m minus 1 Q of d min upon under root 2 n naught, which is equal to m minus 1 Q of d min upon under root 2 n naught. Okay, so therefore the answer is okay. Yeah, so apparently there was some mistake here, so there should be an under root sign, so the answer is this one. So there was a typo in the assignment as well. Any questions here? Okay, if not, then I'll move on to the next question. So this question again was put as a query. I have told this multiple times that allocating different number of quantization levels to different frequency components of a signal according to their information content, different frequency components, which means that you are looking at different frequency bands, which means you will look at a sub band. Then based on their contents, you will look at the information in that particular sub band of the frequency and then do encoding. So based on each sub band of your frequency, you will do encoding. So therefore, this is the way in which you do sub band encoding. This is not the way you do Lempel-Zev or any other Huffman or optimal encoding. Let me move on to the next question now. Okay, so the next question is, an AWGN process is projected over an orthonormal basis with result which basis will result in uncorrelated coefficients. So I have taken this question in week 9. So see question 2 of week 9, but still I'll do it here. That's not a problem. So what we will do is, let's say NT is your zero mean, okay, be your AWGN process. So AWGN process is zero mean. So this is AWGN with zero mean and autocorrelation function Rn of tau as n naught delta tau. Okay, and let's say phi n of t for n equal to 1 to capital N be a set of orthonormal basis okay. So therefore projection of NT on, let me write it I here just to avoid any confusions, on phi I of t is Ni, which is integral minus infinity to infinity nt phi I of t dt. So we need to check if Ni and Nj are uncorrelated. What do you mean by uncorrelated? It means that is covariance of Ni comma Nj equal to 0 for I not equal to j. So we'll just look at the case when your I is not equal to j. So consider I not equal to j, then covariance of Ni comma Nj will be equal to expectation of Ni Nj minus expectation of Ni into expectation of Nj. Okay. Now what is expectation of this quantity, this thing? So expectation of Ni will be equal to integral minus infinity to infinity expectation of Nt into phi I of t dt. Okay, so expectation of Nt is equal to 0. So therefore this part is equal to 0. So this makes this, or this reduces it to expectation of Ni Nj. Okay, so this is equal to expectation of integral minus infinity to infinity Nt phi I of t1 dt1 into integral minus infinity to infinity n of t2 phi j of t2 dt2. So this becomes integral minus infinity to infinity. I can take the integrals common. Let's do one step at a time. Expectation of integral minus infinity to infinity, integral minus infinity to infinity, nt1, nt2, phi I of t1, phi j of t2, dt1, dt2. Now due to linearity of expectation, I can take expectation inside the integrals. Integral minus infinity to infinity, integral minus infinity to infinity, expectation of nt1, nt2, phi I of t1, phi j of t2, dt1, dt2. Okay. So now this thing here is equal to your Rn of t2 minus t1, which comes out to be equal to n naught of t2 minus t1. Okay. So this tau is basically your delay. Here your tau is basically your delay. That is the time difference. So this is what you get. So now if I substitute it, we'll have integral minus infinity to infinity, integral minus infinity to infinity, and not delta t1, t2 minus t1, phi I of t1, phi j of t2, dt1, dt2. Now I can use shifting property on this. So what I'll get is integral minus infinity to infinity n naught delta n naught phi I of t1, phi j of t1, integral minus infinity to infinity delta t2 minus t1 dt2 to dt1. So this integral here is equal to 1. So what we are left with is the remaining part. N naught is constant, I can take it outside. So this is n naught integral minus infinity to infinity phi I of t1, phi j of t1 dt1. So we know that phi I and phi I belong to an orthonormal basis, which means that integral of phi I of t1 into phi j of t1 for all t1 not equal to t, for all I not equal to j will be equal to 0. Okay, so therefore this comes out to be equal to 0. So what we have is covariance of ni and j is equal to 0 for all I not equal to j, which means that ni and nj are uncorrelated. Okay. So an AWGN process is projected over an orthonormal basis will result in uncorrelated coefficients. That is true. That is true. Any questions in this part? Okay, if there are no questions. Okay, let me see what you have put in the chat box. So you have asked, the signal will distort if the transmitted signal bandwidth is greater than the bandwidth of. Where did you find this question?
Ma'am, week 12 assignment, ma'am, this year.
This year week 12 assignment. Let me see.
Ma'am, in last year they have given the answer key, it is multipath channel. This time they have given radio channel.
Yeah, let me see once. Because the options are the options itself are a little bit weird. Did they upload any detailed answers?
Yes, ma'am.
Yeah, let me check. Last year were the options same?
Yes, ma'am.
Just a minute. Want to see what reasoning he gave last year. No, last year also the answer was radio channel. Okay, so I'll tell you what the concept is. Okay, answer is radio channel, that is correct. Okay, I'll tell you what the concept is. So what happens is you transmit some signal xt. I'm talking in time domain. Then you have some channel which is, let's say, ht, and then you have your noise added nt, and then you have your output yt. Okay, so this is your radio channel. So anything between your transmitter and receiver without noise is your channel. Okay, so now what happens is you can model your channel or your receive equation as your xt convolved with ht plus nt. So now in frequency domain, when you go, will be y of f equal to x of f, h of f plus n of f. Right, if you take Fourier transform. So now if you just concentrate on this part, so suppose you have a channel with this frequency response. So this is your h of f. Okay, let's do it in this way. So let's say this is your channel's frequency response. It won't be like this, but still something like this you have. And suppose this is the frequency response of your signal. So this is your x of f, and this is your h of f. The resulting one will be appropriately scaled version that will be located only in this part. Okay, and if you observe, it is constant in this part also. Now
Yes, ma'am.
suppose it's happening like this, ulta, if it is happening opposite. This is your signal bandwidth. This is your signal Fourier transform, and this is your channel. Okay, so now you will get non-zero in this part. So whatever signal was located here was there in these frequency bands will be lost. So you will lose information in these frequency bands. Okay, so any channel through which you are transmitting, if it is behaving in this particular fashion, it will distort your signal. Is it clear? Irrespective of it being multipath channel or whatever kind of channel. Any channel,
Yes.
any h of t which you are having, any radio channel, any channel through which you are transmitting your radio signals, if it's having the situation something like this, it will distort your signal. It's not a multipath specific property. It's in general. Is it clear?
Yes, ma'am.
Yeah. Any other questions?
Ma'am, I have uploaded, ma'am, two questions on portal. Can you check, please?
Which
Today, ma'am, today itself on the portal I have uploaded.
today I had already told you to upload it before 15. I need to prepare things,
Okay, ma'am.
right? So what I can do is I am also a student. So what I can do is if I get when is your exam?
Ma'am, 2 November.
Okay, 2nd November, right? So what I can do is 2nd November means okay, just after Diwali. Okay, what I'll do is in you have I have 1 week time, right? So I'll
Yes,
try
ma'am.
to reply to your mail by let's say 26 or 27. Is it fine?
Okay, ma'am. Okay,
Yeah,
ma'am.
I'll reply to your mail there.
Yes,
I'll
ma'am.
reply to your mail because I haven't
Ma'am,
seen the
actually, it is from practice assignment of ma'am week zero, ma'am. And ma'am, actually, the actual answer may be something else, ma'am. They may have put some wrong answer key in that.
yeah, okay. Let me open what you have done. We have 10 minutes time, so let me just open what you have put.
Yes,
Let's
ma'am.
see. Just give me 2 minutes. You gave it like 20 minutes before the session. You ignore it. It's just like introductory questions so that you become accustomed to the portal. It's not something that is related to the content. It's okay.
Okay, ma'am.
Yeah, you don't have to put too much efforts in that week's assignment. Nothing will come from that. It's not a content based assignment. It's fine.
Okay, ma'am.
Yeah. Anything else?
No, ma'am. Thank
Yeah.
you, ma'am.
Okay. All the best for your exam. Okay.
Thank you,
Thank you
ma'am.
for attending today's session also.
Thank you, ma'am.
Yeah. If you have nothing else, you can leave the meeting.